Welcome to today's episode, where we're diving into the intricate world of distributed systems. We'll focus on some critical elements like time synchronization and state consistency, both of which are essential for developers and engineers working to build resilient systems. As technology evolves, grasping these concepts becomes increasingly important. So, let's unpack the challenges and strategies that can enhance system performance and reliability. Let's start with time synchronization, a foundational aspect of distributed systems. You might think that the clocks across remote machines are perfectly in sync, but that's often not the case. This assumption can lead to significant problems, especially when we encounter time drifts and discrepancies in timestamps. In a distributed environment, each machine operates independently, which can create variations in timekeeping. These discrepancies can be problematic when coordinating tasks or transactions that rely on precise timing. For instance, if two nodes try to update the same piece of data at the same time, unsynchronized clocks can lead to data corruption or inconsistencies. To tackle these challenges, it's vital to implement robust time synchronization protocols that account for potential drifts. Recognizing the limitations of clock synchronization helps developers prepare for the complexities that arise in distributed systems. Next, let's talk about state consistency, another crucial aspect we need to consider. Maintaining a consistent state across distributed nodes is essential, especially during schema changes or network partitions. When changes happen, nodes may not immediately reflect the new state, which can lead to miscommunication and potential data corruption. Imagine one node updating its schema while another is still operating under the old version. They might interpret data differently, resulting in inconsistencies. This issue gets even trickier during network partitions, where nodes become isolated from one another. Without a coherent strategy to manage state consistency, systems can quickly become unreliable. To address this, developers must ensure that all nodes are aware of schema changes and can synchronize their states accordingly. This might involve using consensus algorithms or versioning systems to manage updates effectively across distributed nodes. Now let's face a reality of distributed systems, the possibility of node failures. Nodes can crash or become unreachable for various reasons, like hardware malfunctions or network issues. If these failures aren't managed properly, they can trigger cascading failures throughout the entire system. To mitigate this risk, we need to prepare for failures by employing techniques like heartbeat protocols and circuit breakers. Heartbeat protocols allow nodes to regularly check in with one another, ensuring they're still operational. If a node doesn't respond within a specified time frame, other nodes can take appropriate action to prevent further issues. Circuit breakers monitor the health of services and temporarily halt requests to a failing service until it recovers. This approach helps avoid system overloads and maintains overall stability. As we continue our journey, let's explore how we can test for resilience. To ensure systems can withstand real-world challenges, we introduce testing tools like ToxyProxy and Chaos Monkey. These tools simulate various failure scenarios, giving developers a chance to see how their systems respond under stress. For example, ToxyProxy can create network conditions that mimic real-world issues like latency or dropped connections. By testing how systems behave in these situations, developers can identify weaknesses and address them proactively. On the other hand, Chaos Monkey takes a more aggressive approach by randomly terminating instances in a production environment to test the system's resilience. This practice helps teams understand how their applications handle unexpected failures and encourages the development of more robust architectures. Now let's shift our focus to strategies that enhance system resilience and efficiency, especially when facing connection challenges and potential data corruption. One key strategy we explore is the implementation of a back-off strategy. This allows clients to wait for a specified period before retrying requests after a failure. By doing this, we reduce the risk of overwhelming the system with simultaneous requests, which can lead to further failures. Staggering retries helps systems recover more gracefully from transient issues. To complement this, we introduce jitter, a technique that adds randomness to retry intervals. By incorporating jitter, developers can prevent multiple clients from resuming their operations at the same time, which could create additional load on the system. Another critical aspect of maintaining data integrity is implementing validation mechanisms, like checksumming. Checksums allow us to verify the integrity of data as it moves through the network. By calculating a checksum for data before transmission and comparing it upon receipt, systems can detect any corruption that may have occurred during transit. This proactive approach to data validation helps prevent corrupted data from spreading through the system, ensuring that nodes maintain accurate and reliable information. Finally, we can't overlook the importance of coordination in managing resource allocation and execution plans. Effective coordination helps avoid overload and hotspots by leveraging historical data to make informed decisions about resource distribution. By analyzing past performance and usage patterns, developers can optimize resource allocation to ensure that no single node becomes overwhelmed. This strategic approach not only enhances system efficiency, but also contributes to overall stability. In this episode, we've explored the complexities surrounding time synchronization, state consistency, and various strategies that can bolster the resilience and efficiency of distributed systems. By understanding the challenges posed by these systems and implementing solid solutions, developers can create more reliable architectures capable of withstanding real-world challenges. Join us next time as we continue our exploration of the evolving landscape of technology and the innovative approaches that drive it forward. Thanks for tuning in.